Over next couple of classes, we will study signal space representations of signals. The motivation for this is to facilitate the analysis of digital signal detection and determination of the optimum receiver. Signal space representations of the signals is a very useful and effective tool in the analysis of digitally modulated signals. We will study this important approach and show that a set of signals can always be represented by a set of vectors. Let us begin with signal space and basis signals. So, assuming that we are familiar with the vectors and vector spaces, the concept of vector spaces and basis vector will be extended to characterize continuous time signals defined on some interval, say a, b. Now, an ordered n tuple specified by x1, x2 up to xn is an n dimensional vector. So, if a signal xt can be specified by n tuple, then it too will be a vector. This is basically the principle of representing a signal in terms of vector. Okay. So, let us assume that we have n signals phi 1 t, phi 2 t up to phi n t. Now, these signals are independent, then it implies that none of these signals can be represented by a linear combination of the remaining n minus 1 signals. What I mean is, that is a1 times phi 1 t plus a2 times phi 2 t plus summation plus an times phi n t. If you take the linear combination of all these signals, then this will be equal to 0 only if all ai's are 0. Only if this condition is satisfied, then this set from phi 1 to phi n will be independent. So, let us say that we have a signal xt, and this signal xt can be represented by a linear combination of n independent signals. This phi nt will denote this set of n independent signal by this. So, if I can represent this xt by linear combination, it means I can write like this. This is some coefficients x1, phi t, x2, phi 2t plus xn phi nt. So, this is your time domain signal, and these are some coefficients x1, x2, xn corresponding to this xt. Okay. So, this is equal to now, if every single in a certain signal space can be represented by a linear combination of the independent signals given by this set phi and t, then we have what is known as n dimensional signal space. And this set phi and t is basically known as basis signals. Without loss of generality, let us assume this domain AB to be from minus infinity to plus infinity, and let us assume some constraint on this basis signal as follows. We have phi jt, phi kt integral of this product equal to 0 if j is not equal to k and is equal to 1 if j is equal to k. For sake of simplicity, we are considering only real signals. The same ideas could be extended to complex signals with little modification, but for this course it is not necessary at this moment. Okay. So, if this condition is satisfied, then what we say that this set which we have of basis signals is basically orthonormal. If this was not equal to 1, then it would have been known as orthogonal. Okay, fine. So for any orthonormal set, let us try to determine the coefficients of the linear expansions of a given signal in terms of orthonormal basis signal. So, if we know that I can write my signal in this form, and if we assume that my phi k t's are all is an orthonormal set, then to determine xk, it is very simple. What you have to do is basically multiply both the sides by say phi n t and integrate over the domain minus infinity to plus infinity. So, if I do this on the right hand side also, I would get this as follows. So, now we know that phi k t and phi n t are orthogonal except when k is equal to n. So, do not get confused with this n and this n. This is maybe we could change it, let us change it to say j. Correct? So, only when k is equal to j, this integral of phi k t phi j t dt will be equal to 1, correct. So, from this what we will get is that x j is equal to x t phi j t dt, correct, fine. So, once this orthonormal basis signal set is specified, x t can be represented by this n tuples, correct. So, I can get my x 1, x 2 up to x n, correct. So, what it means that alternatively x t can be geometrically represented by a point in the space x 1, x 2 up to x n, and this is your n dimensional vector. So, what it means that I can associate a vector x with the signal x t. This means that the basis signal x1, this means that the basis signal phi 1 t can be represented by a corresponding basis vector as 1, 0, 0, 0, and phi 2 t can be represented as 0, 1, 0, correct, and phi n t would be represented as 0, 0, 1, correct. Okay, fine. An example of this would be a signal x t which is band limited to say b hertz, correct. Now, this signal can be represented by the sampled version of x t, sampled at the rate of twice b, where b is the bandwidth of the signal. We know that by Nyquist sampling theorem I can write this as where your sinc x is defined by sin pi x upon pi x, correct. And it is not very difficult to show that this set is basically an orthogonal set, correct. So, what it means basically is that this is equal to 0 if j is not equal to k and is equal to 1 by 2b if j is equal to k. So, in this case this forms an orthogonal set, and if you want to get an orthonormal set from this, we can just normalize by the square root of 2b, and then this will form an orthonormal set. So, I can write now my signal x t is equal to where my x k is equal to 1 by root 2b x of, these are sampled version, sampled of at the rate 2b. So, any band limited signal xt can be given in the form of vector as where your xk is the kth Nyquist sample of xt divided by 1 by root 2b. Now, a band limited signal cannot be time limited. Therefore, this implies that you will have infinite number of Nyquist samples. Correct? So, this implies that the dimensionality of this vector space is going to be infinite, because this xk, k will go from minus infinity to plus infinity. So, now let us study another important concept, what is known as orthogonal expansion of signals. Okay. So, suppose that we have a signal st which is a deterministic and real valued, and it is a finite energy signal. So, what it means that if I calculate its energy, this is finite. I can evaluate this integral. Now, assume that we have a set of orthonormal functions correct? And now my problem is to approximate the original signal st, correct, by a weighted linear combinations of this function. So, I want to write s hat t is equal to like this. Now, in doing so, there will be some kind of an approximation error. So, let me denote that approximation error as Et, that would be equal to st minus s hat cap t. Okay. So, now my problem is to select the coefficient sk in the representation of this signal st in terms of orthonormal set in such a way that the energy in this error gets minimized, correct. So, the energy in this error is equal to correct. So, what this implies is I want to choose my coefficients sk in such a way that this quantity gets minimized I can rewrite this as now this can be minimized by taking the derivative of this energy with respect to each of this coefficient S k. Okay. So, let us try to do that. So, my problem is to minimization of this error energy with respect to coefficient Sk. So, what I have to do is take the first derivative of this energy with respect to this coefficient Sk and equate to 0. This I have to do for k equal to 1, 2 up to capital K. Correct. So, this you can easily take the derivative of this, correct, with some respect to some. So, this will Sk will give you I will get a factor of 2 St minus right, and then partial derivative, and then I have to take the derivative of this term inside. This will go to 0 and here basically only Sk will come out. So, derivative with respect to Sk. So, this will be minus phi. So, what we will do, let us take the derivative with otherwise there is a little confusion. So, let us take the derivative with respect to Sj, correct. So, if we do this, basically what I get is Sj here phi j t, correct, dt is equal to 0 for j is equal to 1 2 up to capital K. What we will get from here is Sj is equal to St phi j t dt. Remember this phi n t is an orthonormal set. Okay. So, I will get this. Okay. So, what this means basically that the coefficients are obtained by projecting the signal x t, correct, onto each of the functions phi j t. So, consequently your approximated signal S t is the projection of S t onto the k dimensional signal space spanned by the functions phi n t. So, basically it means that now this error is orthogonal to this space. Okay. So, your E t which is S t minus S hat t, correct, is orthogonal to approximated signal S t, correct. This means this is equivalent to writing E t is equal to 0. Okay. Fine. So, let us quickly calculate the minimum energy for this. So, E minimum from this will be equal to I have to evaluate this, and this can be written as Et St minus S cap t dt. Now we know that Et and S hat t are orthogonal, so this turns out to be this quantity. Okay. So this I can rewrite it as and this is equal to S energy in this minus now this can be easily shown to be equal to summation of these coefficients, okay, because phi kt is an orthonormal set. So when E minimum is equal to 0, it implies that your Es will be equal to this quantity. So when every finite energy signal can be represented by expansion of the form in the equation St is equal to this, and E minimum for that is equal to 0, then the set of this signal phi and t is said to be complete. So my next problem is that I want to obtain an orthonormal set of signals or basis signals from a given set of signals, correct? So this problem we will discuss in the next class. Thank you.